Fins, extended surfaces. Definition: fins are projections protruding from a hot surface to ambient fluid, and they are meant for increasing heat transfer rate by increasing surface area of heat transfer. Example: air-cooled IC engines, reciprocating air compressor, refrigerator and air conditioner units, electric motors and transformers, electronic devices, automobile radiators. Fins are used only when convective heat transfer coefficient are relatively low, that is with the gases or air. Analysis: rectangular fin. This is base wall at T0 temperature. The root of fin is like this. Convection with H watt per meter square. The ambient temperature is T infinity. This qx plus dx, perimeter of this plane is 2 into z plus t, tip or end x equal to L, here x equal to 0, a is equal to profile area is equal to z into t is equal to z into this is z. L is equal to length of fin with z is equal to width of fin, t is equal to thickness of fin. Actual mechanism of heat transfer in any fin is first heat gets conducted from base wall into fin at its root or base, and then while conducting along length of the that is in x direction, heat is also simultaneously convecting from surface of fin into ambient fluid at T infinity with a convective heat transfer coefficient of H watt per meter square Kelvin. Objectives to get heat temperature distribution within fin, that is T is equal to f of x, to get heat transfer rate through fin, Q fin is equal to question mark. Assumption: steady state condition of fin. Consider a differential element of fin of length dx at a distance x from the root of fin, where temperature is at a fin is T. Let Qx is equal to heat conducted into element is equal to minus Ka dt by dx. Qx plus dx is equal to heat conducted out of element is equal to Qx plus dou by dou x of Qx dx. Heat convected from surface of element of fin is equal to H into P dx into T minus T infinity. P is equal to perimeter of fin and is equal to 2 in 2z plus 2t. This is because the surface is in contact. This whole surface is in contact. So for convection we use P into dx as area. For steady state conditions of element of fin, Qx is equal to Qx plus dx plus convection, Q convection. Qx is equal to Qx plus dou by dou x of Qx dx plus h p dx into t minus t infinity. Dou by dou x of minus k dt by dx plus hp t minus t infinity is equal to 0. D square t by dx square minus hp by k into t minus t infinity is equal to 0. D square theta by dx square minus m square theta is equal to 0. Let theta is equal to t minus t infinity. D theta by dx is equal to dt by dx. D square theta by dx square is equal to d square t by dx square. From this is a standard form of second order differential equation in theta, whose solutions can be directly given as this theta is equal to c1 e power minus mx plus c2 e power minus mx. If put m square is equal to hp by ka, where m is equal to root hp by ka. C1 and C2 are constants of integration that can be obtained from boundary conditions. One common boundary condition is at x equal to 0, t is equal to t infinity, and theta is equal to theta naught, t is not theta naught is equal to t naught minus t infinity. The second boundary condition, that is at x equal to L, depends upon three different cases of fin. Case 1, if fin is infinitely long, the temperature at tip of fin will be essentially that of ambient fluid. At x equal to infinity, t is equal to t infinity, theta is equal to 0. And then the solution for temperature distribution for infinitely long fin case is theta by theta naught is equal to t minus t infinity by t naught minus t infinity is equal to e power minus mx. For any fin case, heat transfer rate to entire fin is equal to heat conducted into fin at its root. Q is equal to minus Ka dt by dx. Q fin is equal to root Hp Ka into T naught minus T infinity watt. T is equal to T minus T naught minus T infinity e power minus x plus minus mx plus T infinity. dt by dx is equal to okay. Q fin okay, from this we can get dt by dx. So finally Q fin is equal to root hpk T naught minus into T naught minus T infinity watt. Fin is finite length. Fin is finite in length, but its tip is insulated. Heat conducted into tip of fin is equal to 0. Minus Ka dt by dx is equal to 0. dt by dx at x equal to L is equal to 0. Here, this Q conduction at end will be 0. So d theta by dx at x equal to L is equal to 0. This is one boundary condition. Then solution for temperature distribution for insulated tip case is T minus T infinity by T naught minus T infinity is equal to cos Hm into L minus x by cos HML. And heat transfer rate Q fin is equal to root Hp Ka T minus T infinity tan HML watt. Note, if no case is mentioned in any fin problem, by default assume case 2. In practice, we never insulate the tip of fin, rather we neglect the convection heat loss from the tip. Case 3. Fin is finite in length but tip is uninsulated. Convection heat loss from the tip also. Then the solution for temperature distribution within the fin is T minus T infinity by T naught minus T infinity is equal to cos H m into LC minus x by cos H m LC, where LC is equal to corrected length. LC is equal to L plus T by 2 for rectangular fin. LC is equal to L plus D by 4 for pin fin. Q dot is equal to root Hp Ka into T naught minus T infinity into tan HMLC watt. Q convection tip also. Q convection insulated LC is equal. This is equivalent to the LC L plus D by 4 L plus D by 2 for rectangular fin. Now coming to questions. Here diameter length is given, K fin given 1 and 130 degrees, remaining exposure T infinity is 30 degrees, H given. Heat loss is equal to, here fin is of finite length. Fin is of finite length. So assume case 2. M is equal to root Hp by Ka, P is equal to pi d, A is equal to pi by 4 d square. So root Hp Ka tan T naught minus T infinity tan HML. Tan HML. Rectangular fin is exposure, the fin is uninsulated. Here, so can lose heat from this end also. Everything is given. Then we have to find LC. LC is equal to L plus T by 2 for rectangular fin. Temperature at 30 centimeter from base T theta T minus T infinity by T naught minus T infinity is equal to cos HML L minus x LC minus x by cos HMLC. From that we can get T. Q fin is equal to root Hp Ka T naught minus T infinity into tan HMLC. Okay. Fin efficiency. It is defined as ratio of actual heat transfer rate to taking place through the fin and the maximum possible heat transfer rate that can occur through the fin, that is when entire fin surface is at its root or base temperature. Case 2 heat efficiency is equal to Q actual by Q maximum. Case 2 is equal to root Hp Ka into T naught minus T infinity into tan HML by HPL into T naught minus T infinity. Eta is equal to tan HML by root HP Ka by Ka into L. Eta fin is equal to tan HML by ML. Just remember that eta fin is equal to Q actual by Q max. So Q max is in when whole fin is at base temperature. Entire fin will get to you'll get to only if K of material is fin is infinity. Eta fin case 3 is equal to tan HMLC by MLC. Eta fin directly proportional to root K. Fin material must have high value of K. Example aluminum copper. Aluminum copper. Fin effectiveness epsilon, it is defined as ratio between heat transfer rate with fin and heat transfer rate without fin. Epsilon fin is equal to Q with fin by Q without fin is equal to epsilon fin from case 2 is equal to root hp Ka into T naught minus T infinity into tan HML by when fin is not there, this area A is there, then HA T naught minus T infinity, which is normal. This is T naught, this is T infinity without fin when there is no fin. Epsilon fin is equal to tan HML by root of HA by Kp by tan HML by root of HA by Kp. Effectiveness of fin tells about how much percentage increasing in heat transfer rate we are able to gain by keeping fin as compared to the case where there is no fin. If effectiveness of fin is low, then fins are not worth keeping because they do not help us much in increasing heat transfer. This is the reason why fins are never used with water, because H values with water are very high. Epsilon fin is inversely proportional to root H. Epsilon fin is low. Fins are justified only when epsilon fin greater than or equal to 2. Epsilon fin directly proportional to root P by A. To have high effectiveness, fins must be thin and closely spaced. Thin and closely spaced because it should have high perimeter and less area. High perimeter area means that area which indicates thin cross-sectional area, and closely spaced. Number of fins number of fins required n is equal to total heat transfer required per dissipated by required or dissipated by heat transfer rate through each fin. Epsilon fin directly proportional to root K. Fin material must have high K value. Okay, heat loss in the fin, keeping the entire fin at base temperature is equal to question mark. Here epsilon and eta are given. You just have to remember that effectiveness means Q with fin by Q without fin. Efficiency means Q with fin by Q maximum possible with fin. So here the question is asked about heat loss keeping fin at base temperature, that is maximum. Eta is equal to Q actual by Q max. So Q max we can get it. Effectiveness is okay, equivalent epsilon fin is equal to Q with fin by Q without fin. Epsilon fin is equal to root Kp by Hp HA. If it is of infinite long length, then root of Hp Ka T naught minus T infinity by HA into T naught minus T infinity is equal to root Kp by HA. A metallic rod of uniform diameter and length L connects to heat sources each at 500 degrees. The atmospheric temperature is 30 degrees. The temperature gradient dt by dx at center of bar will be 0. When ends of rods are joined, no heat conduction between ends. Minus Ka dt by dx is equal to 0. Dt by dx equal to 0. Two rods, one length L, other 2L. 100 degrees, 100 degrees. Okay, I think this is previous ESE question. Okay, the temperature at midpoint of longer rod would be question mark. Here what is the two rods maintained at one at 100 degrees. Both ends of longer rods maintained at 100 degrees. One end of short rod is also maintained at 100 degrees, while other end is insulated. Both rods are exposed to same environment at 40 degrees centigrade. The temperature at insulated end is measured to be 55 degrees. The temperature at midpoint of longer would be here is equal to question mark. Here it is 55 degrees. Here also dt by dx equal to 0. Here dt by q convection is equal to 0. So dt by dx is equal to 0. So in both cases 55 degrees only. Unsteady or transient conduction heat transfer T is equal to F of time. Consider a solid body of mass m, volume V, density rho, specific heat Cp, which is at an initial temperature of Ta. Having been heated at a furnace, is suddenly exposed to ambient fluid, which is at a temperature T infinity. M rho V Cp Ta fluid at T infinity, convection H watt per meter square Kelvin. Since body keeps on losing heat by convection, the fluid with a convective heat transfer coefficient H watt per meter square Kelvin, the internal energy of body keeps on decreasing as time progressed, which is manifested by decrease in body temperature of body with respect to time. Let Ti is equal to initial temperature of the body at instant of time. Tau is equal to 0 second, that is when body is just exposed to fluid. T is equal to temperature of body at any instant of time 2 seconds. uh, T is equal to f of time, function of time. Writing energy balance for body at any instant of time t seconds, the rate of convection heat transfer between body and fluid is equal to rate of decrease in internal energy of body with respect to time. HA into T minus T infinity is equal to minus MCP dt by dt. HA into T minus T infinity is equal to minus rho V Cp dt minus dt by dt joule per second. Treating all other parameters including H as constant, now T is equal to F of tau. Separating the variables, tau is equal to 0 seconds to tau. HA by rho V Cp d tau is equal to dt by T minus T infinity. This here tau will come, and here ln of T minus T infinity will come from T to Ta. Then ln of T, putting limits and bringing ln in this side, it will become exponential. Finally, Ti minus T infinity by T minus T infinity is equal to e power Ha by rho V Cp tau. Hence, in any unsteady state heat transfer, the temperature of body changes exponentially with respect to time, as shown in figure. Initially, during cooling, near the end of cooling, and minus dt by dt is equal to rate of cooling is function of time. During unsteady state heat transfer, the rate of cooling or heating of body becomes function of time. Initially, the rate of cooling is very high because of high convective rate between body and fluid due to large temperature difference exists between them. But as time progresses, this rate of cooling decreases due to decreasing heat transfer rate between body and fluid becomes lesser, delta T existing between them. HA by rho VCP second inverse, H rho VCP by HA seconds, time constant of body. T time when body is getting heated. V by A sphere is equal to 4 by 3 pi r cube by 4 pi r square is equal to r by 3. While measuring temperatures of hot gases flowing in a duct by using thermocouple, it must have a very small time constant for which the size of bead must be small. So if a small time constant, so size of bead should be small. He convective heat transfer coefficient H must be high. The his heat capacity of thermocouple material is small. Time constant of a body signifies the time taken by the body in approaching the temperature of thermal ambient, hotter or cooler, when a body is suddenly exposed to it. In above analysis done, it is ensured that it is assumed that temperature of body is uniform throughout its mass at any instant of time. That is, internal temperature gradient within the body are neglected. Such analysis is called lumped heat capacity analysis. T is equal to T is not equal to f of space or location, but T is function of only function of time, not space or location. And both delta T is equal to 0, Q convection. Lumped heat capacity analysis criteria: Biot number less than 0.1, but Biot number H is equal to Hs by K solid. For spheric, S is equal to volume of body by surface area of body is equal to V by A. For spherical body, V by A is equal to R by 3. Biot number is equal to S by Ka by 1 by Ha is equal to internal conductive resistance. Internal conductive resistance offered by the body by external convective resistance. Any metallic body of a reasonable small size, Biot number less than 0.1. Low Biot number values suggest that body offers very little conduction resistance for any internal heat transfer as compared to surface convective resistance, thereby leveling that leveling the temperature difference that may exist between two locations within the body. As the conductive internal conductive resistance is less, heat is almost same. 1D 0 less than x less than equal to L through plane x equal 0 degrees 100 degrees. Okay. But number is equal to HL by K. Okay. White number less than 0.1, but lumped heat capacity analysis is valid. We have to find time. HA by rho V Cp into tau is equal to ln of Ti minus T infinity by T minus T infinity. From that we can get time. The ball temperature after some seconds. Again we can use the same formula. But number less than 0.1. Okay. Just again time required to reach, again we use the same formula, but here immersed in water bath, HA by rho VCP. Here here it is cylinder, so 2 into pi by 4 d square plus pi dl. As this whole area is subjected to convection, and V is pi by 4 d square L, remaining all are same. Spherical thermocouple. Okay, Wyatt number less than 0.1, same formula. The rate of fall in temperature of ball is being asked. So, just to be starting energy balance formula is enough. HA into Ti minus T infinity is equal to minus rho V Cp dt by d tau. At T is equal to 0 seconds only was asked, dt by d tau is equal to, okay. As dt by d tau keeps on decreasing. V by here everything is given, just R by 3 time constant is given, so from that we have to get radius. Okay, what is mean area normal to a hollow sphere? Okay, 2 meters square, 8 meters square. Given temperature difference as the same thick plane wall of same thickness, which is equivalent to normal area. RTH is equal to R2 minus R1 by 4 pi K R1 R2. Okay, KAM AM is equal to 4 meters square. To have lesser heat transfer rate, from the pipe, always keep better insulation. May have a better insulator having lesser insulator material immediately next to pipe. In such a arrangement, R total will be more, RTH total will be more. keep better insulator material outside better insulator material. Okay. Hessler charts are used to determine transient heat flow rate and temperature distribution when during unsteady heat transfer. If Biot number less than 0.1, T is not. In this case, we use lumped heat. T is not a function of space or location, but T is function of time. Delta T tends to 0 between any two locations. Lumped heat capacity analysis. Hessler chart, if Biot number greater than 0.1, then T is a function of space and time. That is, we see different temperatures at different locations of body at given instant of time. Then to get temperature at a given location and at any given instant, Hessler charts are used. Put Biot number equal to 1, ICR is equal to ECR, conduction is equal to convection. Okay, K not be K here, K is varying, K naught plus BT, Q is equal to K A dt by dx, Q by A is equal to K I plus BT dt by dx. As x increases, T increases, K naught plus BT increases. Dt by d, then dt by dx decreases to keep Q by A constant. So it will be like this.